let's say the resistance of the wire was 4 ohms. And let's say, okay, now let's say the voltage of the battery, you're somehow playing with the voltage of the battery and changing it in some weird way. So let's say the voltage of the battery was some weird equation. You see, so let's say you have the ability to play with the dial of the battery in some weird way such that its voltage changes according to this equation. Well, what's going to happen? If the voltage of the battery changes, the electrical field going through the wire is going to be changing. So you actually will create displacement current. On top of that, you will also create conduction current. So we can say at t equals to, we can choose like several different times. T is 1 and t is, let's say, 4. Calculate the I conduction current and calculate the I displacement current. And then B, calculate the B field created, let's say the radius of this wire is, let's say it's 0.1 millimeters. So let's say calculate the B field created inside the wire, 0.05 millimeters from the center, and outside the wire. So if the radius is 0.1, we could say outside the wire 0.12 millimeters from the center. So what we mean is, if this is the wire like this, 0.05 millimeters would be halfway to the edge. So the B field, let's say if the current is this way, if we're looking with our eyes this way, the current will be coming toward you, right? So it's going to be B field, it's going to create is like this. So the B field will be like this inside that wire, right? And outside. So we want to know those, right? So basically any current carrying wire should create a B field due to this equation, mu0 I enclosed. But this equation only will work if the E field is changing in the wire, right? So then let's calculate the I conduction. That one is easy to calculate. I is just going to be whatever the voltage is divided by the resistance of the wire, right? So the voltage over the resistance of the wire. And then at 1 second, what's the voltage? Over 4 ohms, right? So I just put 1 second here, here, and that's it, basically. So this is 2, -4, -2, -8 over 4, so -2 amps. That means the current is actually flowing this way at that time, right? So this is the conduction current, okay? And the other one would be at 4 seconds, right? At 4 seconds. So then you have here 4 cubed minus 4 times 4 squared plus 4 minus 6 over 4. A lot of 4s. Oh, that's good. It's canceled. So 4 minus 6, negative 2 over 4, negative 0.5 amps. Okay, so the conduction current is easy to calculate. Okay, how do you do the displacement current? So the displacement current is going to be E0. So d by dt. So the electrical field in the wire is going to be uniform everywhere in the wire, right? It's just going to be uniform, and it's equal to the voltage difference across the wire divided by the length of the wire. So V over L, right? Remember, electric field is delta V over the distance. So it's the delta V over L. And delta V is this, you see. So when you do this integral, so if this is uniform across the area of the wire, so then this just becomes EA. EA. And then E is equal to V over L, right? D by dt. So this is VA over L. Right? Now, out of these three, which of them are changing? The voltage across the wire, right? One of the three has to be changing in order to create displacement current. Either you should be making the area bigger, right? Or smaller, or you should be squeezing in the wire, or you should be changing the voltage across the wire. Any of the three would work, any three-way. So in our case, area and the L are constant. And then you just have dV dt. Okay, then you put that, take the derivative of that. Okay. Then you have what? dV dt is just going to be 3t squared minus 8t plus 1. Okay, that's good. Now we could just put in the numbers. 8.854 times 10 to the minus 12. See, because of this factor, the E0 factor, that makes displacement current hardly noticeable. So that's why when there is regular conduction current, it will dominate. It will kill this guy. This one will almost be like it doesn't even exist. But when this disappears and there is no current, then this phenomenon is more noticeable. That's why they say capacitor is the ideal example of how this is applied inside of a capacitor, because there is no current. And of course, electromagnetic wave is another classic use of this, because there is no actual conduction current in an electromagnetic wave. It's just a changing E field that's creating a B field. Okay, so there you have here this one, and then the area pi times the radius. Radius was what? 0.00. It was 0.0000001 meters squared. Right, pi r squared, so that's the area. The length was 0.8 meters, right? And now we could put here for 1 second, 3 minus 8 plus 1. Okay.
Wait, that's a quick question.
Excuse me?
Yeah, quick question.
Yeah, of course.
So what exactly is displacement current? Is it sort of like backwards current?
Well, actually, no, that's not that one. No, that's one is it's it's literally not even current, and I don't know why the word displacement current has come out in history, but it's just it acts, changing electric field acts as if it's another source of current through that wire, which it really isn't.
Okay.
Yeah, very good question. Yeah, it's acting as it. In other words, it's another source of creating a B field. So the main way to create a B field is to actually have charges moving.
Mm-hmm.
The other way to create a B field is to change the E field. That's literally what it is. And by changing an E field, we mimic as if there is a actual current flow.
Mm-hmm.
So it's actually not backwards current. It's actually not current at all.
Got it. Oh, yeah, because I was gonna say because a lot of this just sort of sounds like, oh, it might be from similar to like Lenz's law, but no, it's different.
Oh yeah. No, that's not this,
Yeah.
because that one is actual current flow. Yeah,
Right. That's
yeah. It's not that. We're gonna start that Monday.
Right.
Yeah. Good question. Yeah. Okay, so okay. 8.854 times pi times 0.00. Well, it's going to make it so small, pi 0.0001 squared. Divided by 0.8 times 10 to the power 12 minus. Okay, so this portion of it already comes out so small, 3.477 times 10 to the minus 19. And of course, this portion is just negative 4, so times 4. So negative 1.39 times 10 to the minus 18 amps. So it has units of amps, but it's actually not current at all. Okay, so now for 4 seconds, then we would just basically put 4 here, and it might actually change the sign of the current. So now we'll have 4. Yeah, so then we'll still have this thing, 3.477 times 10 to the minus 9. So then 3 times 4 squared minus 8 times 4 plus 1. Yeah, it's probably going to be positive. Yeah. So then it's going to be 3 times 16 minus 32 plus 1 times 3.477. So 59.109 times 10 to the minus 18 amps. Okay, so if I want to know what is the B field created inside the wire 0.05 millimeters away, so then what's the B field inside of a wire? Well, if it's uniform, which in this case it is, right? In other words, the E field at the center and over here and over there, it's all the same, right? And the current is uniform. So then it's just going to be our equation. If we're inside, then it's going to be mu 0 I over 2 pi r squared r if we're inside, right? So then you just use here 4 pi times 10 to the minus 7 over 2 pi r squared is going to be 0.0001 squared, and then r is going to be your 0.0001 1, 2, 3. This is 4 zeros, 5. It's half of this basically, right? 0.00005 over 0.001 squared. Okay, then what's the I? Well, then it's gonna be the sum of the conduction current and the displacement current. So you see, I'm combining these two things. This is conduction current, and then this guy is displacement current. So then once I found this and once I found this, I can combine them, right? So in our case, the conduction current was -2 amps. And now the displacement current at 1 second was this, -1.39 times 10 to the minus 18. I think when you do this on your calculator, it's just going to tell you that it's -2. In other words, this hardly affects this. See, I don't think it's even going to change it. 2 negative minus 1.39 times 10 to the power 18 negative. You see, -2. It doesn't have enough power to compute that because this is so small compared to the actual current. So then that means it disappears, and then you just multiply it by that, 0.00005 times, and this is 2 times 2 divided by 0.0001 squared times 10 to the power 7 negative. Oh, that's pretty strong. -2 milliteslas. That's a pretty strong field, actually. And the fact that it's negative means the current, since the current was flowing this way, the field is like this. Instead of being like that, it's this way, like that. Okay, what's going to be the field at 0.12 millimeters? Well, the only difference is instead of this equation, this is still going to be the same because this is going to dominate over that, right? And then it's just going to be this thing, 2 times 10 to the minus 7. But instead of r over 2 pi r squared, what is it? It becomes your regular mu0 I over 2 pi r, right? So it becomes just this thing over 2 pi r, and then r is this one, 0.00012. Is that right? 1, 2, 3. Yeah, that's true. 0.00012 times the I. And then what's the I? Well, just -2 again. Right? Yeah, that's it. 2 times 2 divided by 0.00012. Right, so 1, 2, 3, 4. Okay, so it'll be 1, 2, 3, 4. Then it'll be -3.33 milliteslas. Right? Yeah. So it's actually bigger than the inside the wire at that location. -3.33 milliteslas. So then if we want to do this whole thing again for 4 seconds, what's the difference? Well, instead of -2, you just use -0.5. But then this one this one, when you add it to the negative 0.5, it again doesn't do anything to that guy. You see, this still completely kills this. So that means that you're just gonna just put here negative 0.5, and you're just gonna put here negative 0.5, and that's it. And otherwise, the answer is gonna be very similar. So the fact that this was positive and this was negative, it's not really gonna affect the D field because it's hardly noticeable anyway. So in order for this to be more noticeable, what needs to happen is we have to create a situation where the current is zero, right? The current is zero. And one of the cases that could happen is like in a capacitor.